This quiz focuses on how the hyperparameters ALPHA and affect the MultiTaskElasticNet model in scikit-learn. We'll be investigating how tuning these parameters impacts the model's coefficients and overall performance. It's all about understanding the effects of regularization. I'm using MultiTaskElasticNet to predict 3 different things. Target variables, simultaneously, using 10 different input values, features. The goal is to find the best way to balance keeping the model simple, regularization, and fitting the data. This involves carefully adjusting ALPHA and this describes the setup and the task. I'm using a tool called MultiTaskElasticNet from the scikit-learn library, which helps handle multiple output problems. I need to understand the role of 2 settings, ALPHA and, to get a better model. This statement is incorrect. A higher ALPHA means stronger regularization, which makes the model's coefficients smaller, not larger. This is correct. Controls the blend of L1, lasso, and L2, ridge, regularization. Moving closer to 1 means LASSO's effect gets stronger. This is false. When ALPHA is 0, there is no regularization. This is correct. A tiny ALPHA means almost no regularization, and a near 0.5 suggests an even mix of lasso and ridge, making it behave much like a standard linear regression model. This section would discuss the combined effect of the alpha and L1 ratio parameters. ALPHA is a master control for how strong the regularization is. I can think of it as a volume knob. A larger ALPHA turns regularization up, making the model simpler. Acts like a mixing knob. 0 is all L2, ridge, regularization. 1 is all L1, lasso, and anything between is a blend. This question explores how changing the ALPHA and hyperparameters in scikit-learn's MultiTaskElasticNet affects the model's behavior. I'll examine how these parameters influence the model's coefficients and overall performance. Think of it as adjusting the knobs on a complex machine to fine-tune its output. Absolutely, that's correct. Increasing towards 1 increases the influence of L1 regularization, which encourages sparsity, setting some coefficients to exactly 0, in the model. Think of it like this. You're telling the model to simplify itself by using only the most essential features. You got it. A very small ALPHA means that regularization is weak or essentially turned off. With near 0.5, the balance between L1 and L2 regularization is even. Therefore, the model will behave quite similar to a standard multitask linear regression model with minimal constraint on the coefficients. It's like removing the training wheels from a bike. The model is free to learn as it wants. Nope. Increasing ALPHA actually does the opposite. It strengthens regularization, forcing the model to shrink the magnitude of its coefficients towards 0. This helps prevent overfitting. It's like tightening the reins on a horse. It restricts the model's ability to overreact to noisy data. That's not quite right. Setting ALPHA to 0 completely disables both L1 and L2 regularization. This means the model will be free to fit the training data as closely as possible, which can lead to overfitting. It's like letting the horse run free without any guidance. This is the overall theme of the quiz, understanding how to adjust the hyperparameters, ALPHA and within MultiTaskElasticNet to achieve the desired model performance. I see alpha as a dial controlling the overall strength of regularization. A higher alpha value means stronger regularization. I'm essentially telling the model to prioritize smaller coefficients. A lower alpha value means weaker regularization, allowing for larger coefficients. Alpha is the hyperparameter that determines the overall strength of regularization in the model. It's like a master control knob for how much I want to penalize large coefficients. A larger alpha means stronger penalties, leading to smaller coefficients and a simpler model. A smaller alpha means weaker penalties, allowing more complex models with potentially larger coefficients. Think of it as a volume dial for shrinkage. L1 underscore ratio is a lever to precisely balance the two types of regularization: L1, lasso, and L2, ridge. Lasso drives some coefficients to zero, creating sparsity, while ridge shrinks all coefficients toward zero. The L1 underscore ratio is a value between 0 and 1. 0 means all ridge, 1 means all lasso, and values in between represent a mix. I use this hyperparameter to fine-tune the balance between sparsity and shrinkage. This hyperparameter, L1 underscore ratio, controls the mix of L1, lasso, and L2, ridge, regularization techniques. I can visualize it as a sliding scale. At 0, it's pure ridge, at 1, it's pure lasso, and in between it blends the two approaches. A higher L1 underscore ratio leads to more lasso behavior. More coefficients become exactly 0. This statement is absolutely true. I'm increasing L1 underscore ratio, which directly increases the effect of lasso regularization. That means my model will tend towards simpler models with more coefficients driven to exactly 0 for feature selection. This is also true. With a small alpha, I'm barely penalizing the coefficients. Furthermore, an L1 underscore ratio near 0.5 means I'm balancing L1 and L2 equally. These combined effects minimize the impact of regularization, making the model almost the same as standard multitask linear regression. This is false. Increasing alpha increases the strength of regularization, which actually leads to smaller asterisk, not larger, coefficient magnitudes. That's false. When alpha is 0, regularization is completely turned off. My model becomes a standard multitask linear regression without any penalty for large coefficients. I see alpha as a dial controlling how strongly we penalize large coefficients in the model. A bigger alpha means stronger regularization, pushing coefficients towards 0. Think of it like a volume knob. The higher you turn it up, the quieter, smaller, the coefficients get. This slider mixes two types of regularization: L1, lasso, and L2, ridge. A ratio of 0 is pure ridge, 1 is pure lasso, and in between values blend both. Lasso pushes some coefficients to exactly 0, creating a sparse model. Ridge shrinks coefficients toward 0 but keeps them all non-zero. These are the numbers our model learns to multiply the features by. Their magnitude shows the importance of each feature. Sparsity refers to how many coefficients are exactly 0. High sparsity implies the model is using only a subset of the input features. Both alpha and L1 underscore ratio directly affect this. This is the core quiz question about understanding how alpha and L1 underscore ratio impact MultiTaskElasticNet, a scikit-learn model used for multiple regression problems. This statement is false. I've learned that a larger alpha actually decreases the coefficient magnitudes, because it strengthens regularization. That means the model is penalized for large coefficients. I found this statement false, too. Setting alpha to 0 means no regularization. That's like removing the penalties, resulting in a standard linear regression model. This is correct. Increasing L1 underscore ratio increases the influence of lasso, pushing the model towards more sparse solutions, more zero coefficients. This one's true. A tiny alpha and an L1 underscore ratio near 0.5 mean barely any regularization, almost like a standard multitask linear regression model. I'm investigating how changing the alpha and L1 underscore ratio hyperparameters in scikit-learn's MultiTaskElasticNet model affects the results. Specifically, I want to understand how these changes influence the model's coefficients and overall performance. It's all about finding the sweet spot for regularization. This statement is false. Increasing alpha actually does the opposite. It decreases the magnitudes of the coefficients. This is because a larger alpha strengthens the regularization penalty, pushing the coefficients towards 0. Think of it like this: a stronger penalty discourages large coefficients. That's true. The L1 underscore ratio hyperparameter directly controls the balance between L1, lasso, and L2, ridge, regularization. When you increase L1 underscore ratio, closer to 1, you put more weight on L1 regularization, which is known for creating sparse models, many coefficients become exactly zero. Nope, this is false. Setting alpha to 0 means there's no regularization at all. The model becomes a standard linear regression model. No penalty for large coefficients. This is true. With a small alpha, regularization is weak. An L1 ratio near 0.5 indicates a balanced mix of L1 and L2 penalties. The net effect is that the model behaves very similarly to a standard multitask linear regression, with minimal shrinkage of coefficients. It's almost like the regularization is barely there. I see alpha as the overall dial for how much regularization I want. A higher alpha means stronger regularization, pushing the model's coefficients towards 0. Think of it like a tightening grip. A small alpha means a loose grip, letting coefficients be larger. It's all about controlling how much the model is penalized for complexity. The L1 ratio is like a mixing knob. It decides how much L1 regularization, lasso, versus L2 regularization, ridge, I use. A ratio of 0 means pure ridge, 1 means pure lasso. In between, it blends both. Lasso likes sparsity, forcing some coefficients to exactly 0. Ridge likes to shrink everything towards 0 but not necessarily to 0. These are the learned parameters that the model uses to make predictions. They're influenced directly by alpha and the L1 ratio. Larger alpha means smaller coefficients overall, while the L1 ratio controls the balance between forcing some coefficients to 0 and simply shrinking them. These coefficients show how much each feature influences the predictions. This is the core question. I want to understand how these two hyperparameters, alpha and L1 ratio, influence the MultiTaskElasticNet model's behavior and resulting coefficients. It's like tuning an instrument to achieve the perfect sound. This refers to the overall problem. I am adjusting the alpha and L1 ratio parameters of a MultiTaskElasticNet model, a type of linear regression for multiple output variables. The goal is to find the best combination that achieves a balance between accuracy and model simplicity, avoiding overfitting. This highlights that alpha and L1 ratio don't work in isolation. They interact to determine the final model behavior. For instance, a large alpha will always lead to smaller coefficients, regardless of the L1 ratio's value. Understanding these interactions is key to properly tuning this model. I control the balance between L1, lasso, and L2, ridge, regularization. A value of 0 means pure ridge regression, a value of 1 means pure lasso regression, and values between 0 and 1 blend the two. Think of it as a mixing knob. The closer you turn it to 1, the more lasso flavor you get. It's all about finding the right mix. I control the overall strength of regularization. A higher value means stronger regularization. I'm pushing the model coefficients towards 0 more aggressively. Think of me as a volume knob for the regularization. The higher the volume, the stronger the penalty for complex models. Setting me to 0 completely turns off regularization. This quiz challenges your understanding of how the alpha and L1 ratio hyperparameters affect a MultiTaskElasticNet model. MultiTaskElasticNet is a powerful tool that combines L1 and L2 regularization for multiple regression tasks simultaneously. I let you tune regularization strength and the balance between L1 and L2 to find the optimal model for your specific problem. Both alpha and L1 ratio influence how the model learns. Alpha decides how strong the regularization overall is, while L1 ratio specifies how much each regularization type is contributing to that total effect. This is the core question. You need to decide which statements accurately describe how changing alpha and L1 ratio changes the behavior of the MultiTaskElasticNet model. This statement is true. As you increase L1 ratio towards 1, you shift the regularization more towards lasso, which tends to produce simpler models with some coefficients set exactly to 0, promoting feature selection. This is also true. A very small alpha weakens the impact of both L1 and L2 regularization, and a L1 ratio near 0.5 provides a balanced blend between them, making the model behave similarly to a regular linear regression model because there is very little penalty applied to the model coefficients. This is false. Increasing alpha strengthens regularization, leading to smaller asterisk, not larger, coefficient magnitudes. This is also false. When alpha equals 0, both forms of regularization are completely disabled, leading to a standard multitask linear regression model that will fit the data with no constraints.